Welcome to Math with Malia. Today we're going to cover Savvas enVision Algebra 1, Topic 10, Lesson 6, Operations with Functions. By the end of this lesson, you will be able to add, subtract, and multiply different functions. Let's take a look at the Explore and Reason. The graphs of f of x, shown in red, and g of x, shown in blue, are below in the picture. We can see that they're both parabolas, as they are both quadratic functions. And g of x in blue is 3 units up from f of x. We can see that the vertex is at positive 3. So how do the domain and range of each function compare? Well, for f of x, the domain is all real numbers as the graph goes infinity to the left and towards infinity to the right. For g of x, it is also all real numbers, okay, as the graph continues to the left and continues on to infinity towards the right. How about the range? Remember, the range are all possible output values, and so we need to look where the minimum is, as these are both upward-facing parabolas. For f of x, we have our minimum at 0, so our range is y can be anything greater than or equal to 0. But for g of x, our vertex has shifted up 3 units. So all possible y values can be anything greater than or equal to 3. Graph another function in this form where you add a constant to the whole function. This again will give us a vertical translation. So if we're adding a function, it would move either up or down. And so we can graph something with a vertex that would be possibly at 6, or it could even be below the function at -1. So when we're only adding a constant to the whole function, when we are shifting it vertically, only the range is changing. The domain will still be all real numbers, but only the range changes as we are adding that constant c to the outside of the function, or outside of the parentheses. Example 1, adding and subtracting functions. So just like we have added numbers and expressions and polynomials before, we can also add functions. And it's pretty straightforward. Just like we add polynomials, we can line up the terms and combine like terms and then have our new function. So here we have function f in red, 2x minus 3, and g of x in blue, 2x squared plus x plus 7. And we're just going to combine the like terms. So I'll highlight them in different colors. We can see that we only have one quadratic term, so that gets to the front so we can have our answer in standard form. And we're adding 2x and a positive x. Okay, so that gives us 3x. And then we're going to add our -3 constant and our positive 7 constant. So adding -3 plus 7 gives us positive 4. So just make sure you're lining up the like terms. If you want to rewrite it and do it like an addition problem, I'll show you how to do that. You can rewrite the larger function or the function with more terms on the top, and then the second function will go underneath, and just make sure that you line up the linear terms underneath the linear terms, the constants underneath the constants. So I've shifted f of x over, and then I'm just going to add them together, just like I do a regular addition problem. 1x plus 2x is 3x, and 7 minus 3 is positive 4. So either method works. If it helps you to stack them on top of each other and line up the terms, that might be beneficial. Okay, just make sure you're watching the signs. Okay, example 1. How do the domain and range of f plus g compare with the domains of the original functions before we added them together? So let's take a look at f of x. F of x, we can see, is a linear function. The slope is positive. So I'm just going to draw a rough sketch of what that graph would look like. Okay. it would be upward slope. And since it's linear, the domain continues all the way to the right and all the way to the left. So the domain would be all real numbers, or negative infinity to positive infinity, and the range would also be all real numbers. Okay, for g of x, we have a quadratic function. So it would be shaped like a parabola. And it is upward facing since our leading coefficient is positive. So the domain would also be all real numbers as the graph continues on to the left and all the way to the right. But the range would be determined by that minimum value at the vertex. So you can plug in this function into your y equals on your graphing calculator and you can find the vertex. The vertex would be at 6.875. So our range would be anything equal to or greater than 6.875, as that is the minimum. When we added the two functions together, we got 2x squared plus 3x plus 4, another quadratic function. And so that, of course, would also be an upward-facing parabola as our leading coefficient is positive. So we're going to have another upward-facing parabola. So the domain would also be all real numbers. And the vertex would be determined by that minimum. So we could solve graphically or algebraically. And typing that equation into our y equals on our graphing calculator, we would get that minimum value at 2.875. Okay. So in general, when we combine functions, the domain and range might be different than the original functions. Just make sure you check to see what kind of new function you get after you've combined them. Example 2, subtracting two functions. So now we're going to do g minus f. Notice we're going to do the quadratic function minus the linear function. Okay, and so again, just making sure that we line up the like terms. So in the example they gave us, just remember that negative outside the parentheses, there's an invisible -1, so we're going to distribute that -1. Each term inside the parentheses becomes the opposite sign. You can also line them up vertically if that helps. So you can line up the like terms, and I'm subtracting, so this would be a -2x, and I'm subtracting a -3. So 2x minus 0, that gives me 2x squared. X minus 2x gives me -x. 7 minus a -3, well, the opposite of -3 is +3, so I'm actually going to be adding 3. This gives me +10. So don't forget you're subtracting that whole binomial. Okay, so when we subtract those, we still get a quadratic term, even though one of the original functions was linear. The domain, again, is all real numbers, and the range is determined by the minimum of that parabola. So since it is an upward-facing parabola, my leading coefficient is positive. Okay, so we know it's going to be upward-facing. We need to calculate that minimum value that at the vertex to determine the range. Everything will be greater than that value. All right, your turn to try it. We're going to subtract f minus g. So our f function is the quadratic function. So I'm going to write that first. I'm going to stack them vertically because I think this is helpful. I'm going to subtract g of x. So 11x needs to be lined up underneath my other linear term, and my constant needs to be underneath the other constant. Okay. 15x squared minus 0 stays 15x squared. -x minus 11, I'm subtracting, so -8x plus -11x is -19x, and 4 minus 6 is -2. All right. Example 2, multiplying functions. You can think of this just like multiplying polynomials. Okay, so we're going to be distributing each term in the first binomial by each term in the second binomial. So remember your FOIL method. First, outer, inner, last. So multiplying the first term by the first term in the second binomial. Then you multiply the first term by the last term in the second binomial. Then you do the inner terms, 20x times, so 20 times x. And then you do the outer terms, 20 times 5. Combining your like terms, which are usually the linear terms, and making sure your answer is in standard form. If you want to use the area model, I'll demonstrate that for you. Okay, so we have two binomials. That means we're going to have a 2 by 2 area model. And I'm going to write the first binomial on the top, so 9x and positive 20, and the second binomial going down the side, x and positive 5. And now I'm just calculating the area of each individual box. 9x times x gives me 9x squared. X times 20 gives me 20x. 9x times 5 gives me 45x. And 5 times 20 gives me 100. And then we would make sure we combine our diagonal terms. Those are the like terms, the linear terms. So we will just write our final answer in standard form, moving from the upper left corner to the lower right corner. 9x squared, 45x plus 20x is 65x plus 100. Okay, so you'll get the same answer, whichever method works best for you. Part B, are the domain and range of the functions f and g the same as the domain and range of the product of those functions? Okay, well, both the original functions were linear, so the domain and range would both be all real numbers. But when we combined them by multiplying, we got a quadratic function. And a quadratic function changes the range. The range will have a limit determined by the vertex. In this case, since our function is upward facing, it's a positive parabola, or the leading coefficient is positive, so it will be an upward facing parabola. So then this would be our minimum point at the vertex. So all possible y values, or the range, will be equal to or greater than that value at the vertex. The domain is still going to be all real numbers, as we have arrows on the end of our functions. It continues on and on to the left and on to the right. Okay, time to try it. We're going to multiply two functions and describe the domain and the range of the product. Part A is a little tricky. We need to take a look at this square root of x function and rewrite it in a way to use rational exponents. So this comes from a previous topic, I believe topic 6. So we can rewrite the square root of x as x times, or x to the 1/2. Okay, and we're multiplying that by 2x minus 1. Now, x to the invisible 1 is the same as x to the 2 over 2. You'll see why I'm using that, because remembering our exponent rules, if we are multiplying like bases, what do we do with the exponents? Well, that means we add the exponents. And in order to add the exponents, I need to have a common denominator. So that's why I changed x to the 1 to x to the 2 over 2. They're equivalent, but I know that I'm going to have common denominators to be able to add the exponents. Okay, so x to the 1/2 times 2x would give me 2x to the 3/2, because 1/2 plus 2/2 is 3/2. And then x to the 1/2 minus 1 is just going to be minus x to the 1/2. And now I can rewrite that, put them back into radical notation. So 2, and remember, I'm doing a little bit of a review here. Remember, when we're using rational exponents, whatever is on the denominator, that is the root, the type of root that we're doing. So in this case, the root would be a square root. And whatever's in the numerator, that is going to be the exponent to the radicand, or whatever is inside the square root. So then it would be x cubed, because the exponent to the radicand would be 3. Okay, That's a little review on rational exponents. And then x to the 1/2 we know is the square root of x. So that one was a little tricky, but it was a good review from topic 6. Okay, let's try letter B, and I'm going to use the area model for this one. Actually, I don't need to since I just have one term for g of x. So let's just write it algebraically. 2 to the x times 3x squared plus 4. I'm going to be multiplying. Now, if I am multiplying, I notice that this 4 is a base 2. I can change that to have a base of 2. So I'm going to rewrite it. So it has a base of 2. Whoops. It's not squared. I did not write that correctly. 2 to the x, this is squared, and 4 is the same as 2 squared. So 2 to the x times 3x squared, there's no like terms. We're just going to multiply them. We're just going to write them like this. Okay, but I did change 4 to be 2 squared for a reason, because now I have a common base. I have a base 2. And remember, if we're multiplying bases that are the same, we add the exponents. So this would be 2 to the x plus 2. Okay, how about the domain and range for these? Well, for part A, it looks like we have some kind of a square root function. And our square root function has a domain of everything greater than or equal to 0. And our range does have a limit. If we graphed it, if we typed this into our y equals on our graphing calculator, we would see that the range would be everything greater than, but not equal to, greater than negative 0.27. Okay, I'll separate these. Okay, and for part B, our domain, again, we have this very complex function when we combine them. Our domain is going to be all real numbers. Because we have an exponential function. And since it is exponential, we are going to have an asymptote, and that asymptote will be at 0. So the range will be anything greater than 0. It never approaches the asymptote. So it might be helpful for these to graph them on your graphing calculator so you can get a picture of what the graph would look like, and then you could determine what the domain and range are. Example 3, let's apply function operations to a real-world situation. Here we have a cylinder. It tells us that the height is twice the radius. So I'm going to write that down. I might need to know that for later. So the height is 2 times the radius, or 2r. The cylinder is sealed at the top and the bottom to form a container. Find a function for the total surface area of the container. So I'm just looking for everything on the outside of the container. If I were to wrap it in wrapping paper, what is the perfect amount of paper that I would need? What dimensions would yield a total surface area of about 120 feet squared? All right, so first we need to formulate our equation for the function. That is the surface area of just the top and the bottom. So we can see that the top and the bottom are circular. So we know the area of a circle is pi r squared. And since there are 2 circles, we're going to multiply that by 2. Okay, then we're going to come up with our function for the lateral sides of the cylinder. And if we were to unroll the cylinder, the area around the circle, or the circumference, would be the length of that rectangle, and then we could multiply that by the height. Okay, so circumference, remember, is 2 pi r, and then we're just going to multiply that by height. I'm glad I wrote this down, because height is also 2 times the radius, so we can already substitute 2r for our height in our equation. And then if we simplify, 2 times 2 is 4 times pi, and r times r gives us r squared. Now, if I'm talking about surface area, I'm going to then add the area of the base plus the area of the lateral sides, okay? So the area of the top and the bottom plus the area of the sides. Okay, so that's what we have here. We're adding them together, and we can see that pi r squared is a common term. So we can just add those like terms and get a total of 6 pi r squared for the total surface area. Okay, then it's asking what dimensions or what values for r and h would give us a surface area of about 120. So if this equation, 6 pi r squared, represents the surface area, we could plug that into our graphing calculator. Okay, type that into your graphing calculator. And then we could use our trace function and trace along that graph to where y equals 20. And from there we can estimate what the x value is. It should tell us what x is at about 120. So using your graphing calculator, you can see that when x is about 2.52, that's where you would get a radius of 120. I think they labeled the axes wrong. This should be radius. And this should be total surface area. Okay, but again, using your graphing calculator is very helpful. So just using your trace function to find where the y value is 120 or close. And then that would be your radius. Now, what about the height? How did we figure out the height? Well, remember, height is 2 times the radius. Okay, so then we just need to double that value, 2 times 2.52, and that will give us our approximate height of 5.04. So if the cylinder has a radius of 2.52 and a height of 5.04, if we plug those into our formula here, 6 pi r squared, it would give us approximately 120 feet squared for our total surface area. All right, try it. Suppose the cylinder in example 3 is not sealed, and so it only has a bottom. It does not have the circular area on the top. What dimensions would yield a total surface area of about 120? Okay, so let's remember, we took the lateral surface area plus the area of the base. And since there's only one, we're not going to multiply it by 2 this time. Okay, so the lateral surface area was 2 pi r times the height, right? Circumference times the height. And the area of the base is a circle, so it's just pi r squared. We remember still that the height is 2 times r. So I'm going to rewrite this, and instead of h, I'm going to multiply by 2r. And then I can simplify. 2 times 2 is 4. I have pi r squared again, plus 1 pi r squared. So now my formula is 5 pi r squared for total surface area. Now when that is equal to 120, we can just use our opposite operations and solve for r. So I'm going to divide both sides by 5 pi. And that will give me r squared. And then, of course, to get r by itself, I need to take the square root of both sides. So in your calculator, you're going to do the square root of parentheses 120 divided by 5 pi. And your radius would be approximately 2.76 feet. And the height, remember, is double that. So your height then would be approximately 5.52 feet. So those dimensions would give us a surface area of 120 when there was not the circular cover on the top. All right, we've made it to the concept summary. Functions with operations are very similar to polynomials, so just remember to match up your like terms and use an area model if that's helpful for you when you are multiplying your functions. Let me know if you have any questions, and I'll see you back here for lesson 7.